In this video, we learn about second order homogeneous differential equation with constant coefficients. We consider the case where the characteristic equation has rare and repeated roots. Consider the second order differential equation giving us ay double prime plus by prime plus cy is equal to 0. Then its characteristic equation is giving us ar squared plus br plus c is equal to 0. So here, since the roots are repeating, r1 is equal to r2, and so the general solution will be giving us y of t is equal to c1 er of t plus c2 multiplying t er of t. Example 1. Solve the IVP giving us y double prime plus 6y prime plus 9y is equal to 0 with the initial conditions y of 0 is equal to 2 and y prime of 0 is equal to minus 1. To solve this given differential equation, our first step is to form the characteristic equation. So we're going to take the coefficients in here. So here we have 1, we have 6 and 9. And so the characteristic equation will be giving us r squared plus 6r plus 9 is equal to 0. Factorizing this equation gives r plus 3 multiplying r plus 3 is equal to 0. And so we have the root to be r is equal to minus 3. And so this root is repeating. Since the roots are repeating, our general solution will be giving us y of t is equal to a constant c1e exponent minus 3t plus a constant c2 multiplying t, then e exponent minus 3t. We now compute our particular solution by substituting in the initial conditions. So with the first initial condition, we have y of 0 is equal to 2, and so we are going to have 2 is equal to c1 e exponent 0 plus c2 multiplying 0 e exponent 0, and so c1 is equal to 2. So with our second initial condition, we need to compute y prime of t. So now let's differentiate y of t. Y prime of t will be equal to minus 3c1 e minus 3t, then plus, so to differentiate this term we have to apply the product rule, and so we are going to have c2 out, then e minus 3t, then minus 3t e minus 3t. We now substitute this initial condition into a given expression, so we are going to have minus 1 is equal to minus 3, c1 is known to be 2, then e, t is now 0, plus c2 e exponent 0 minus 3 times 0 e exponent 0. Simplifying this gives minus 1 is equal to minus 6, then plus c2. Thus c2 is equal to 5. Hence our particular solution is giving us y of t is equal to c1, which is 2 e exponent minus 3t, then plus c2, which is 5 times t e exponent minus 3t. Example 2. Solve the IVP y double prime minus 4y prime plus 4y is equal to 0 with the initial conditions y of 0 is equal to 1 and y prime of 0 is equal to 0. Our first step is to form the characteristic equation, so we are going to have r squared minus 4r plus 4 is equal to 0. Factorizing this equation gives r minus 2 multiplying r minus 2 is equal to 0. And so we have r to be equal to 2, and so the roots are repeating. Thus our general solution y of t is equal to c1 e exponent 2t plus c2 multiplying t e exponent 2t. Now let's find the actual solution. So we have to substitute in our initial conditions. With the first initial condition, we have y of 0 is equal to 1. Thus we have 1 is equal to c1 e exponent 0 plus c2 multiplying 0 e exponent 0, because t is now 0. Thus c1 is equal to 1. Now let's find c2. With the second initial condition, we have y prime of 0 is equal to 0. So we need to differentiate our general solution y of t. So let's differentiate y of t. y prime of t will be giving us 2c1e2t plus, with the second term we use the product rule, so we're going to have c2 out e2t plus 2 times t e2t. We have the initial condition to be y prime of 0 is equal to 0. Thus, we have 0 is equal to 2, c1 is known to be 1, then e exponent 0 plus c2 e exponent 0 plus 2 times 0 e exponent 0. So this simplifies to 0 is equal to 2 plus c2. Thus, c2 is equal to minus 2. Hence, our particular solution is y of t is equal to c1, which is 1, e exponent 2t plus c2, which is now minus 2 times t e exponent 2t. We may choose to factor out e2t, so that's e2t out 1 minus 2t. So this is our particular solution. With our third example, we have to solve the IVP. 9y double prime minus 12y prime plus 4y is equal to 0, with the initial conditions giving us y of 0 is equal to 0 and y prime of 0 is equal to 3. The characteristic equation will be giving us 9r squared minus 12r plus 4 is equal to 0. Factorizing this gives 3r minus 2 multiplying 3r minus 2 is equal to 0. So solving this gives 3r minus 2 is equal to 0. Thus, r is equal to 2 on 3. And so our general solution will be giving us y of t is equal to c1e exponent 2 on 3t plus a constant c2 multiplying t e exponent 2 on 3t. Now let's solve for a particular solution. With the initial condition, we have y of 0 is equal to 0 and y prime of 0 is equal to 3. Substituting the first initial condition, we are going to have 0 is equal to c1 e exponent 0 plus c2 times 0 e exponent 0. Thus, c1 is equal to 0. Now let's solve for c2. So to solve for c2, we have to differentiate y. So that's y prime of t will be giving us 2 on 3 c1e 2 on 3t plus c2 out, then we use the product rule, so that's going to give us e 2 on 3t, then plus 2 on 3t e 2 on 3t. But c1 is equal to 0, and so this guy will go to 0, so that's this will go to 0. Thus, y prime of t will be equal to c2 out e 2 on 3t plus 2 on 3t e 2 on 3t. From the initial condition, we have y prime is equal to 3 and t is equal to 0. Thus, we are going to have 3 is equal to c2, then e exponent 0 plus 2 on 3 multiplying 0 e 2 on 3t. Thus, c2 is equal to 3. Hence, our particular solution is giving us y of t is equal to c1, which is 0, then e 2 on 3t plus c2, which is 3 times t e 2 on 3t. Thus, we have y of t to be equal to 3t e 2 on 3t. Thank you for watching. See you in the next video.